work. I'm so proud of me. Back to the action. Well, at least the notes are up there now, and so there's a record of it. Okay, sampling distribution was all positive. Let me show you what I mean by this. Lots of pennies in here, right? Lots of pennies. This right here is a 1, 2, 3, 4. That's one sample, right? Of a possible 5 pennies. If I graphed this one, take the average, take 1 penny out, set it over here. That's a different one, right? I keep those 4. There's a different one. There's a different one. I could do that about 6,000 times, keep these 4 and do a different one, right? I'd get a lot of different things up there. Then what I have to do is take these 4, set them aside, pick a new group of 4, and do the exact same thing all over again. Every single possible combination of 5 pennies. If I did that, that's a lot of combinations. That is, oh my gosh, that is so big. That's 6,000 permute 5. Would you like to know what 6,000 permute 5 is? 6,000 permute 5. I can't believe how big that's going to be. Clear, quit, clear. Come on, clear. Math, probability. Whoops, clear. Answer 6,000. Math, probability, choose 5. It's 6.5 times 10 to the 16th power possible combinations. That's a 6 with 16 zeros after it. That's a big number, right? Could you imagine that many of these little green X bars up here? What would that graph look like? Well, whatever it looks like, that's what this is talking about. A sampling distribution of every single possible combination. If you graph every single possible combination, it would be at a ridiculously large number. But Max was right when he says it looks like a bell curve. It's going to make a perfect shaped bell curve. It doesn't take that many samples to get there. We'll show you what I mean by this today. But sampling distribution is all possible combinations. There are 3 of these terms that are easy to get confused, and they're right here. What is the difference between the distribution of a population? I'm going to call that number 1. The distribution of a sample, that's going to be number 2. And then the sampling distribution of a sample statistic, oh my God, that was 6 words. Seriously? 6 words. And I love to say it real fast. Sampling distribution of a sample statistic. Sample distribution of a sampling mean or sampling proportion are the 2 different kinds of statistics. But today we're going to look at the sampling distribution of sample proportion today. We'll do that today in class. And that just sounds like too many words to actually be a real thing. Here's what number 1 is. The distribution of a population, okay, is the distribution of population. That's what all the data looks like. All of the data. If I 1 penny at a time, graphed all 6,000 pennies, that's 6,000 X's on a graph. I think I told you what this would look like a couple of times. It's bimodal, big hump over in the 80s, 90s, and I'd have a big hump over in the 2010 era. About 10 years ago when I started teaching this class, I got a lot of pennies. I got 2 big gluts full of pennies. There's some that are in between. There's a 2021 penny in here. There's a 1956 penny in here, right? But if I graphed every one of these, I'd have this bimodal distribution, 2 big humps in it. Okay, like a camel, a dromedary. That's what the distribution of a population is. It's the data itself. Number 2, the distribution of sample. Okay, this one is what my small sample looks like. So to compare, distribution of a population is all the data. This would be 6,000 pennies. This one, just my 5 pennies. If you made a graph of just your 5 pennies, that's what the distribution of a sample is. Just your sample, what it looks like. And then we get to number 3, the really wordy one. This is the sampling distribution of a sampling statistic. We'll have 2 kinds of this. We'll have a sampling distribution of a sample mean and a sampling distribution of a sample proportion. Wow, that's wordy. That's the one that's all possible samples of a specific size. Okay, we're not going to talk about unbiased estimators because we don't have to this year because nobody's taking the AP exam. Thank God. Down on the bottom, we're not going to talk about the size effect of population, and we're not going to talk about this guy, but we are going to talk real quick about reduced variability of a statistic. If I want to have less variability, and I want my graph to get, what was the word we used, more smushed? Yeah. If I want my sampling to be more smushed, you remember what it is I have to do that? How do I get a more smushed graph? This was sample 1. This was sample of 5. Do 20? How about 2 million? As long as it's bigger than 1, right? The bigger your sample size, the smaller your spread. And so if you want to reduce variability, you increase sample size. Hopefully that makes sense. I want to figure out the average height of a person at Meridian High School. I go out and I test 10 people, right? Would you feel better if I tested 100 people? Yeah, because they're going to be more likely to be close to that true average height. Okay, you're going to get less variability the more you sample. Okay, that one's not rocket science. And so in general, bigger samples equals less variability. I wonder to myself, one of the tasks you had to do with your homework, and some people struggle with this at first, and I totally get it, was estimating standard deviation, okay? Here's a population down on the bottom that goes from like 1950 up to like 2020. That's about 70 years. Do you see the 70 years right there? 70 years. If I wanted to figure out standard deviation for this population on the bottom, I just take that 7 years divided by 6. It's about 6 standard deviations to get from one end to the other, right? So I'm saying the standard deviation for my penny thing down here is around 12, maybe 11. I'm ballparking it. I don't really know, but I'm just kind of throwing it out there. This standard deviation up here is smaller. This one goes from 1980 to about 2005. From 1980 to 2005 is 25 years. Okay, 25 years. Take your 25 years, divide it by 6, I get about 4. That's got a standard deviation of about 4. This one had a standard deviation of about 3. Notice we chopped it, like divided by 3. We made it smaller. I wondered, is that predictable? By taking a sample size of 5 times as big, maybe 2 or 3 that I changed the standard deviation by. Could you determine ahead of time, I want to only have this much range? Could I figure out how much I have to sample? And the answer there is yes, you totally can. It's 100% possible to determine ahead of time how big I want this spread to be and how much you have to sample in order to get there. Like every election presidential poll, every single one of them says the same thing at the very end of it. It says this poll is good, plus or minus 4%. Every single time, I guarantee you, it'll say plus or minus 4%. How do they come up with plus or minus 4%? Because plus or minus 4% is the exact thing you'll get with a sample size of 1,000 people. Whether it's Pew Research Center, or Gallup. These are companies, Pew and Gallup, that are respectable, okay? They are people that do this for a living. Hopefully you know by now, the idea of getting accurate data and sampling is not an easy thing. It is very difficult to do. People do not like to take their time to answer questions in polls, and they don't like to share their data. And that's becoming even more so now with the concept of Google and Apple being all over our lives 100% of the time, right? People do not want to share their data. They don't want their information given. So it's becoming even harder to get good data. But there are companies that do this for a living. That's what they do. They're called Pew, P-E-W, and the other big one is called Gallup, G-A-L-L-U-P. Anytime you see a Pew or a Gallup poll, that's respectable. When you see NBC News poll, not so much. When you see Fox News poll, not so much. Okay, these are news organizations that don't do this for a living. All they do is grab information from sources and spit it back out at you. Okay, but Pew and Gallup, those are ones that you see and you're like, okay, I believe those numbers. And every time they go out and they do a poll and you see plus or minus 4%, that almost automatically means 1,000 was the sample size on the question that they asked. So it's sort of standard to go out and ask 1,000 people. That's why you get plus or minus 4 all the time. So these are predictable, and we can show you the math behind it on why it works that way. There's one little extra note we need to throw in about this. And it's kind of a dirty word that comes up every now and then, that it's not something people want to deal with, but it's a reality. There's a however here. However, if your sample is more than 10%, like you go crazy sampling. If I went out and I sampled 100 Meridian students out of the 450 or 500, that's more than 10%. Okay. If your sample is greater than 10%, you shouldn't attempt inference. This is breaking what we call the independent clause. If you sample too much, you're affecting the population. Okay, 6,000 pennies. A lot of pennies, right? Now, talking just on probability sense, if I pull a 1956 penny out of here, right, and I go like this, have I drastically altered the probability of pulling out another 1956 penny when I tell you there's only one in there? Well, yeah, it's 0 now because it's already gone, right? When you sample, you change the population. Every time you took 5 pennies out of here, this became a different population than it was originally. It's easy to do this with smaller numbers and things like jelly beans, you know? So I've got 40 jelly beans. 10 of them are red. Wesley really likes the red ones. You like the red jelly beans? Yeah. So he goes for the red jelly bean. There's 10 of them in here. He takes a red jelly bean out. His probability of randomly pulling a red jelly bean would have been 10 out of 40 or 25%, right? Then I go over to Jenna and offer you a jelly bean. He pulled a red one. Is it still 25% that you'll get a red one? It's changed. It's only 9 out of 39 now, right? So what we say is when you sample, they're not independent of each other. His sample affected what population you were left with. If you sample too much, I decide to pull out that many pennies, which is everything I can put in 2 hands right there. There's like $5, $6 worth of pennies right there. That's 10% of the population. If I take out more than 10% of the population, then we say that population right there is drastically altered, and I shouldn't be doing inference by taking more samples because I took too much. You follow what I mean? Once you take too much, it's way changed and different. I've altered it too much. Taking 5 out of 6,000 is not more than 10%. That's not so bad. That's okay. You're not altering it a ton. But 10% is sort of our cutoff. So when you take bigger sample sizes, you don't want to go past 10. And so, for example, and this will come up on a homework question, if there's 500 people here on campus, what's the most I should ever sample? Well, 10% of 500 is 50. I shouldn't sample more than 50 people. If your population is 10,000, I shouldn't sample more than 1,000 because then you're changing the population. You can't take another sample. All right, let's flip on over and start talking about proportions. Now, way back at the very beginning of the year, Whoa, that's the Wayback Machine when we were like talking to each other on Zoom. God, I hated that. That sucked so bad. We talked about two kinds of data. There's two kinds of data that we always deal with. One of them is categorical data. Categorical. Categorical data comes at you naturally in percents. We call these percents proportions. Categorical data will always yield proportions. When you talk about people's favorite colors, those are categories: red, blue, yellow. And then you'll report them as percents. This percent like red, that percent like blue, and so on. The other kind of data that you'll deal with is not categorical. It started with a Q. Ooh, do you remember what the Q one was?
Quantitative.
This is quantitative. Quantitative data, you can add them up and divide. Like our pennies here are quantitative data. This is over on the March 22 to 26. We'll do this one next week. Okay? Quantitative data we call means. You'll hear these two words over and over and over now. In fact, these are the only two types of problems we'll deal with every single day from now until the end of the year. We'll either call it a proportion problem or you'll call it a mean problem. What we're going to do today is we're going to investigate the sampling distribution of a sample proportion, percentages. Okay? So, we're going to look at Reese's Pieces. Do you like Reese's Pieces? You're kind of like, meh. Does anybody in here go crazy for chocolate and peanut butter together, like Reese's Peanut Butter Cup? Yeah, see, it's the dudes. I do too. Not the pieces, but you like Reese's Peanut Butter Cups. Yeah, chocolate and peanut butter to me is just like, that's a match made in heaven right there. Whenever I buy the bags of candy for Halloween, the big giant bag with mixed stuff, I like pull out all the Reese's Peanut Butter Cups, and then I feel really guilty about it, so I have to throw like one or two back in. But then the rest go in my freezer. Just love them to death. They're the bomb. They're the best. Okay, what I have is a machine. This is my machine right here. You can see it's got the little twisty dial on it. It's full of Reese's Pieces, not peanut butter cups, Reese's Pieces, the little dudes. Do you know what colors Reese's Pieces come in? Yellow, brown, and orange. Did you know that most of them are orange? 45%, according to what they report. There's more orange. I think it's because the orange dye is cheaper than the yellow and the brown. But anyway, so I've got this set up here. It says the probability of drawing an orange is 45%. We're going to pull 25 candies out, okay? 25. And look at the percent, because it's categorical. We're talking orange. We're going to look at the percentage of them that are orange, okay? So I'm going to animate this thing, and it's going to look just like this. Here we go. Ready? We're going to draw a sample out. It's pulling out oranges and yellows and browns, and what I got was 32% in my sample. That was 8 of the 25, and it put a little dot right here above 0.32, okay? That's one sample. One sample. It came in low. But that's sampling variability. That's totally going to happen. I'm going to do it again. Draw another sample. And it threw, oh my God, it was exactly the same. It was another 0.32. What are the odds? Not good, but it can happen. Here comes my third sample. Be different than the first one, will you? Oh, this one was 40%. It put a different dot right here. This was 32, 32%, and 40%. If I take the average of those three, 32, 32, and 40, it's right there. It's 0.347. Do you believe that? A little bit higher than the 32, but closer to the 32 because there's more of them there. So that's what this mean is. Also, it's calculating a standard deviation for me for those 3 dots. There are 3 separate samples. And here comes another one. Do you like watching the candy machine kind of spit them out? Or does it get boring? Okay, it's totally boring. I'm going to turn the animate off. That's 4 dots down there. That one came in at, let's see, what was that particular one? 49%? Oh, 52. It says right here, 52%. I'm going to go ahead and pull 6 more samples out all at once and not animate it. Here we go. You ready? Boom. Now I should have 10 dots down here. There's my 10 dots. You're supposed to look at those 10 dots and go, that doesn't look like a bell curve. Does that look like a bell curve? No, it totally does not look like a bell curve. That's a pretty good indication that sampling 10 or taking 10 samples of 25 is really not enough data. That question will come up today. How much data is enough to say, oh, bell curve. Okay, well, I'm going to keep those 10, and I'm going to now throw 90 more on top of there. Here's 100 samples, 100 separate samples. I got a lot of candy. Actually, I'm not going to lie. My candy machine is infinite. It never runs out. So here comes 90 more dots. Is it getting bell curvy yet?
A little bit.
Just a little? Higher on the middle, lower on the sides? A lot of it?
Yeah.
Does it feel bell curvy yet? That's 100 dots. Let's add 900 more and make it 1,000 dots. You ready for 1,000 dots? Boom. There's 1,000 dots. Getting bell curvy yet? Like the normal curve bell curvy? Things you should notice. I told you before we started that the oranges made up 45%. Right there, 0.45. What's the average of all my samples down here? Oh, it's 0.45. Does it make sense if it's 0.45? And so the sampling mean, or the mean of the sampling distribution, this is a sampling distribution of a proportion. The mean of this will be whatever that says. That totally should make sense. That's what should be in the middle. How about the standard deviation? 0.097. That's like 0.09. That's like 0.1 either way is my standard deviation. That means standard deviation of about 10% for 0.1. Does that look like about 60% from that end to that end? This is probably like 15. That's probably like 70. It's in that ballpark. It's about 6 standard deviations wide. About 60% is my total range from the bottom to the top. That's 900 for 1,000 total dots. Let me tack another 0 on here. Here comes 10,000 dots. Ready for 10,000 dots? There they are. There's 10,000 dots. Did it get even more bell curvy? I can put the graph on there and you can decide for yourself. Does that look like the normal approximation right there? It like fits perfect, doesn't it? It's not close. You can get really crazy and you can throw 100,000 dots on there. There they are. There's 100,000 dots. It's got a mean of 0.45 and a standard deviation of exactly 0.1. We're going to write this data down. Here it comes. I'm going to put it on our piece of paper and then we're going to try some other stuffs. So right over here we had N was 25. That was our sample size. We had the true proportion of orange Reese's Pieces at 0.45. And we're going to write down the shape, the center, and the spread. Shape, center, spread. Well, what shape did it look like when I graphed all these suckers? Hopefully you say that that looked like it was approximately normal. Approximately normal. The center of this distribution, let me take another look at it. The center of the distribution, where was the dead center of it? Oh, it's right there, 0.45. And hopefully that makes sense that whatever this is, this will be the exact same 0.45. The spread was 0.1. We're going to change things up and not do samples of 25. Now we're going to do samples of N equals 50. What happens when I make the sample exactly double the size? How are we doing on time? It's 10:31. We're out of here at 11:25. We have like 15 minutes. As soon as I get this thing done with the candy thing, make sure I kick you out. Like stand up, move, go to the bathroom, all that stuff. Okay? Don't let me forget, because sometimes I'll start talking and I'll just keep yabbering on. We're going to do the same analysis: shape, center, and spread. Shape, center, spread. But now we're going to try 50. Oh, I need to make that bigger for you. Is that better? Okay, here comes sample sizes of 50. I'm just going to reset everything. Okay, reset. We're going to change our sample to 50, and we're just going to pull 1 out. So I'm doubling my sample size. I wonder what will happen to spread. Predictions. Let's see, you got a prediction? When you double the sample size, what do you think will happen to the spread? It'll get smaller. Do you think it'll cut in half? Wouldn't that feel good? Like double the sample size, cut the spread in half. That'd be nice, right? That would be super sweet. That's like, oh, I can remember that if I just sample twice as many and the spread chops in half. We'll see. Okay, we're going to sample twice as many. Here comes 1. There's my 1. It came out at 42%. It was a little bit less than the 45%, which is the real deal. There's 1. I'll throw 9 more dots on there. I always like to just throw a 0 on the end. It makes life easy. Here's 10 dots. Doesn't feel very bell curvy yet, does it? Still doesn't look very bell curvy. Think it'll look like that when I throw a 0 on the end and make it 90 more for a total of 100 dots? We'll see. Feeling bell curvy? There's 100 dots. Here comes 1,000 dots. Does my mean get pretty close to 0.45 right there? I'm narrowing on 0.45. What about this? It was 0.1 before, right? 0.1. We were hoping it would chop to 0.05. It's 0.069. That's not really half, is it? Oh, crap. That's not going to work out. I'm sorry. I apologize, but it doesn't. Sample size doubled. The spread does not cut in half. There is a formula for it, though. Here comes another 0 on the end. Ooh, how bell curvy are we feeling? It's a little sloppy, but it's pretty bell curvy, right? That's a technical term, bell curvy.
I'm gonna say bell curvy. That's the real
bell curvy. So I'm going to turn that off. Here comes 10,000 dots. Boom. Feeling pretty belly curvy. Take a notice. Our mean, 0.45. This was 45%. I had 45% of those suckers inside of that thing that were orange. The mean of all those little samples, right on 0.45. I buy that. Ooh, 0.07. Sorry, Alyssa, it didn't come out to be 0.05. It would have been nice if it was 0.05, but it's totally not 0.05. I'm going to write this stuff all down, and then we'll move to the last one. It's all rigged. Lies, damn lies, and then statistics. Okay, it does look approximately normal. The center didn't go anywhere. It was still 0.45, but the spread was 0.07. 0.07. It didn't chop in half. Would have been nice if it chopped in half. I would have liked that. Last one we're going to do is we're going to change our sample size to 200. Not breaking the 10% rule because I've got infinite Reese's Pieces. Wouldn't that be cool to have a candy machine that had infinite candy in it and you never ran out? I mean, besides growing to 400 pounds, which I'd probably do if it had the right candy in it.
And I think maybe
What's that?
maybe it's like 400 pounds.
Yeah. Does everybody have their 400-pound candy? Mine actually isn't that. Mine would be gummy something.
I like sugar. It needs the looks.
Gummy bears? You know what it would be? When I was younger, it would have been Sour Patch Kids. I could eat Sour Patch Kids until the roof of my mouth started to bleed from the granules just tearing it apart.
Mine would be Three Musketeers.
Three Musketeers is your 400-pound candy. So if you just had an endless supply of Three Musketeers, you'd be 400 pounds.
Yep.
Anybody else got one?
No, mine's the Sour Patch.
Sour Patch Kids?
Watermelon, Sour Patch watermelon.
Yes.
Oh, yes.
Yeah, Sour Patch Kids, watermelon
The
ones.
watermelon.
Yeah.
Is that sort of like the God, what is the there's the pink Starburst are better than the other Starburst, right? Pink Starburst.
Pink and red are the best.
You can actually buy bags of just the grapefruit Starburst.
No way.
You can't
Totally
buy the
can.
Starbursts that are like the little ones that are not individually wrapped though. Those
The
aren't fair.
Starburst,
Oh.
the tropical ones.
You have to get the ones that are like individually wrapped, normal size Starbursts.
Have you had the Starburst jelly beans?
What?
Yeah, I don't
They're really close to Jelly Bellies. They're
No,
sweeter
like
than
when
normal
they
jelly
change
beans.
that. Like they just
So.
need to keep it simple. Just keep it original.
Just keep it simple, she says. Yeah, yeah. Okay, we're gonna try sample sizes of 200. We'll take a look at what happens to the spread. Something interesting is going to happen. Something noteworthy is about to happen, which is gonna say, hey, that's predictable. Really? Okay, we're gonna change our sample to 200. There's 200. We're gonna clear off this dude, leave that proportion, and we're just gonna start off with our 1. Here's our sample size of 200 of them. Whoa, got 43%. Got pretty close to the mean right off the bat, the very first one. That's pretty cool. There's actually sort of a weird inverse thing. The spread gets farther in the actual count, but you get closer to the actual average. Yeah, anyway. Okay, here comes 9 more. Here's 10 samples. There's 10 dots. Still not feeling very bell curvy. I'm gonna turn that dude off. It did animate it. I didn't want it to animate it. Here comes one more. There's 100 dots. What's my spread doing? 0.036. Really? 0.036? Where did that come from? 0.036. Here's 1,000 dots. Boom! Feeling bell curvy? It's a little all over the place, isn't it? I mean, it's kind of making a bell curve, but yeah, look at that. Man, if that was your hair in the morning, you'd just be like, that's Sunday morning where you don't have to go out the house, right? Here's 10,000 dots. 10,000 dots. Oh, it got a lot better. Okay, that's pretty good. We go with bell curve. Let's see, good bell curve. Yes, that feels good. Notice what our spread is right here, and our standard deviation was 0.035. 0.035. I'm going to write this stuff down. Shape, center, spread. The shape is still approximately normal. The center was at 0.45, no change there. Here's the spread, 0.035. 0.035. Whoops, it's off the edge, isn't it? Okay, here's the deal. Don't say it out loud because it's time for us to take a break. When we come back, what we'll do is we'll answer this question. Depending on our sample size, there's a 25, a 50, and a 200. Can you make some sort of prediction about how making the sample size bigger, how does it affect the spread? What do you do with your change in order to figure out what's going to happen to the spread? Okay, go take a break. Go to the bathroom, walk around, do some yoga, take attendance, come up with a story about what Olivia's doing today. Olivia is at the mall, sipping Starbucks, buying shoes.
Olivia is probably
I got better the
sleeping.
first time.
She's sleeping.
Probably. Yeah. If I call her, she probably won't answer. But what?
Pictures of fun stuff.
All right, I'm going to go to the bathroom myself because I don't want to wet myself in front of the class. That'd be bad.
Okay, do you want to be in
Who needs a job? Somebody needs a job. Dane, I got a job for you. The little bowl over there next to the knockout prize box.
Can I put the pennies back?
Yeah, all the ones that have been sampled go in here. They're tainted. They've been sampled. Don't put them in the big one. They go in the little one. Thanks, man.
Hey, you took my parking spot.
Did I?
Yes.
I'm sorry.
The past 2 days.
Did I do it yesterday? Did I?
Yes.
Okay, so next time I won't.
Thank you.
Thanks.
No, it's like I've been parking there since like the very beginning.
Okay,
And then yesterday, I was like, who took my parking spot? And then I see you in your car today, and I was like, yeah, I'm gonna call him out.
I don't think I can add any more people. I think I broke it.
No, you're gonna.
I'm trying.
I'm sure it's just a bunch of stuff that's not even gonna be done.
Well, I'm gonna send you the thing.
Oh, is it that thing Carissa's doing?
No.
Oh. She's been texting me.
No, I think
And I
Trey-
haven't sent it in.
I think Trey put it together, and I think it's
I have
It's because his mom is.
Yeah, no, I got that already too.
Oh, you got that?
Yeah, I got that. Wait, what picture?
I sent it to you. Why is mine blurry? They're all supposed to. Everybody.
Yeah, no, I saw that.
Nice.
I forgot who sent that to me.
I don't know. There you go. I don't know if we can. Oh, I dropped it. They would have added you. I already got that. There you go. You're in it now. So you're welcome.
What is Olivia?
Come on, you got it.
I have to because we're looking for it.
Good. You're gonna have the best time of your life. Thanks, Hal. Just kidding. I don't know. It's supposed to be fun. I'm excited.
Where are we even going again?
Idaho. We're going to Silverwood and where else are we?
Are we all
going?
back already? Everybody waiting on me?
Some like event center thing. It's gonna be cool.
Are you going?
Players are really- Come on.
It might be fun. It might be fun.
It'll be fun.
The other ones
Well, convince them to go. We need our whole class to go.
Okay.
You're not going? What did they say? The parents are going?
Oh, I heard your parents are going. I was like, what?
What you want them to go? I think there's only like one parent, maybe two. Like I think Rachel and Andy is going. But if they need a second parent, they
Okay.
will. But if they don't, then.
Anybody formulate any ideas?
It's pretty chill.
Here, I'll give you a minute. Talk to somebody else about it. If you got an idea, share it with somebody else and maybe they'll go, no, that's dumb. That way you don't have to publicly ridicule yourself. Pen.
You're.
What do you think?
Where do you want me to?
The standard deviation, how does it change when we make population bigger? Can you predict it? That doesn't sound like standard deviation, chat.
It went.
Sorry.
It sounds like somebody's got a prediction. You got a prediction?
Oh no.
Okay, so this one, well, I don't want to point at it. You tell me. What do you think's happening here? It's definitely getting smaller. That's 10%. That's 7%. That's 3.5%.
That one half of that.
This one is definitely half of that one.
But that, I don't know what the relationship to the point was.
This one doubled in size,
Yeah.
and that's, well, 25% less than that one. About. It's not 25%. It's actually 30% less. It's not 25%. It's about 30% less. This one went times 4, and that one was half. And I'll guarantee you that is exactly half of that.
That's nice.
Half feels good, right?
Yep.
Half feels good. So do you think that's times 4? So it's half of the times 4 is divided by 2?
Yes.
Something is happening to the 4 to chop it into 2. It's not cut in half, though. It's a sort of a weird thing. Do you know how to turn 4 into 2? Well, you can subtract 2. You can divide it by 2. And then there's what this is. How do you turn 4 into 2 in a weird way? It's not divide 2. What's that? Times by half would be that's the same as divide 2. It's not that one, but you're thinking. That's good.
Square root.
Say that again. I heard it.
Square root.
Square root. Can you turn 4 into 2 with the square root?
I mean,
Yeah.
that one in a while.
Yeah. In fact, that's it, dude. It's totally a square root relationship. Because this is times 4. Wait a minute. What about that to that? Let's see if this works. This dude right here, how many 25s go into 200? How many quarters make $2?
8.
That's 8. I wonder what the square root of 8 is. That's 2.82. If I take 0.1, 10%, and divide it by that, 1, here, I'll do it. 0.1 divided by the last answer. Did it work? 0.035, 0.035. It is 100% divided by the square root of the change in that, which is a little bit weird, which is why you don't have to ever remember that. You'll be able to use your calculator, and we'll show you how to do it with the calculator, okay? But it's pretty slick. In fact, almost all the stuff we'll do will be in here, and you won't have to memorize a lot of weird formulas. There's a couple things you'll have to write down, and we'll show you what those are. Okay. Based on the candy machine, applet, and penny activity, describe what we know about shape, center, and spread of sampling distribution of a sample proportion. Whoa, that's a long word. Sampling distribution of a sample proportion. What do we know about those? And this is all these X bars you just put up here with size 5. Okay? We know that the shape will be approximately normal. Okay? It will be approximately normal. We'll get to sample size, how much you actually have to sample. The center is easy. The mean of all your samples, the little p-hats, every one of your samples, your p-hats, is equal to what the true mean really is. It's really 0.45, so the center of that was 0.45. It's really 0.45. The center still stayed 0.45. That doesn't change. It just is what it is. Here's the one that gets a little bit screwy. What about the spread? We know that bigger sample size equals smaller standard deviation. The mathy term, the mathy way to say this, is it varies inversely as the square root of the size change. Ooh, that sounds awful. Varies inversely as the square root of the size change? Yeah, you won't have to do that. That's just the relationship. That's the mathy way to say that you divide by the square root of whatever your change is. Okay, big important question. When is it okay to say that we got approximately normal? You probably heard me say, does that look like a bell curve? No, it doesn't feel very bell curvy yet. Technical term, bell curvy. When did it get bell curvier? What has to be true? Here's our official rule. We can say that when 2 different things happen. The first one is that n times p is greater than 10. The second one is when n times 1 minus p is greater than 10. Both of those things have to be true. Now, this is a mathy thing, and we'll show you the mathy thing when we do an example together. But what it means is you're expecting to get at least 10 affirmatives and 10 negatives. With the Reese's Pieces, when I sampled, my sample size is big enough if I expect to get 10 orange and I expect to get 10 that are not orange. Okay? If you expect 10 of each, at least 10 of each, then you're sampling enough. Okay? Sampling 3 is not going to do it. If I pull 3 Reese's Pieces out of my machine, am I going to get at least 10 that are orange and 10 that are not orange? Well, no, I'm not even getting 10. If I pull 10 out, will I get 10 of each? No. How about 20? If I pull 20 Reese's Pieces, is it possible to get 10 orange and 10 not orange? Yeah, but do I expect it? Not at 45%. I'm going to come up short on one. The sample size required for the Reese's Pieces problem is a little bit more than 20. Okay? It's like 24, 25. To do that, to say that eventually you're going to be approximately normal. If you have this part and this part to be true, then you can say approximately normal. The technical way the easy way to say it is need 10 expected yes and no's. You got to get 10 expected yeses and no's in order to say that you're going to be approximately normal. Are you sampling enough? Okay, the mean and standard deviation of the sampling distribution of a sample proportion. There's that word again, sampling distribution of a sample proportion. The mean of all my p hats, we already told you was p. It's whatever p is, that's going to be the mean. That's going to be in the dead center. Whatever proportion you expect to get, that's the proportion that will be in the middle. The standard deviation, all your p hats, here's the formula, and it's a winner. Big fraction bar, p times 1 minus p on the top over n, all square rooted. Yep. There we go. Square root, fraction bar in there. We're going to have a relationship with our fraction bar on our calculator today. We're going to love it, and it's going to love us back. It's like Moulin Rouge. You guys know the movie Moulin Rouge? There's no greater thing in the world to be loved and love in return. And you're going to have that relationship with the fraction bar in your calculator. You're going to love it, and it will love you back. All right. When we go to work on real problems, and we're going to show you 2 real problems today. The first real problem is going to be over here. It's going to talk about vouchers and schools and kids planning on, this is the 4-year college one. This principal is going to go out and sample students and ask them, are you going to a 4-year college? The other one's going to be about out in the community. There is a person who wants to do a thing to ask people how they feel about vouchers. So we'll get to vouchers, and we'll talk about vouchers today. You guys have voucher discussions like in Lawrence's class or anywhere? Controversial societal stuff. We'll talk vouchers. We're going to get to these 2 problems. Whenever we dive into what we call an inference problem means we're going to take a sample, then make a decision based on the sample. Okay? Take a sample, make a decision. That's inference. Anytime we do an inference problem, you have to check what's called your conditions. There has to be things that are true in order to do inference. Every time I do an inference problem, I always check my irons. This is a handy-dandy word. We'll use it a lot. When you check your irons, you're checking to see if it's independent, if it's random, if there's outliers, are we approximately normal, and is there any strong skew? That's it. All the inference we do, those are the things we'll have to check. Some tests and some things will require things you don't have to check. It makes it nice. The only 2 you have to do for proportions is you have to check the R and you've got to check the N. In the proportions problems that we will examine, you've got to know the R and the N are taken care of. The R, is there a random sample? Was our sample random? If we did not randomize in the way that we sample it, we're screwed. Okay? Random sampling is super, super important. Otherwise, I can just totally get lazy. Someone told me to go out there and ask 6 people randomly, what we should do for prom. I'm like, cool, I'll ask these 6 people, I'm done. Are you 6 right here in front of me representative of the whole high school? That's being lazy then, because I'm not getting a good random sample to make sure everybody's got the opportunity to have their opinions heard. The N down here stands for this. Data is approximately normal. In order to do inference, we have to be dealing with approximately normal data, or we're wasting our time. There's 2 checks we'll do with this. I wrote them down up previously. They're that NP is greater than or equal to 10, and N times 1 minus P is greater than or equal to 10. Those are the 2 things that must be true every time we go to do inference. All right, are we ready to dive into a real problem? Realness? Let's get real. Because I'm tired of being fake. This is a real true to life inference problem we can solve with the stuff that we just talked about today. Well, we don't really solve things. We never prove anything in stats. We just give somebody a probability and tell them to run with it. Okay. Am I going to make billions of dollars by selling this vaccine? There's a 98% chance of it. Should you do it? Probably. I mean, if I'm a CEO, I'm going to run with that, right? But that's what statisticians do. We just give you a percent, and then you got to make a decision. Okay, here's the story. A superintendent of a large school district wants to know what proportion of middle school students in her district are planning to attend a 4-year college or university. Suppose that 80% of the middle school students in her district are planning to attend a 4-year college or university. This is God coming down and telling us it's really 80%. Does that really happen in real life? No, because God doesn't speak to you. And if God does speak to you, I'd like to file some complaints. What is the probability that an SRS of size 125 will give a result within 7 percentage points of the real value? And so what we're doing is we're starting from a point of knowledge, meaning that it's really 80%, and we're going to figure out the probability that if we take a sample size of that much, you might miss by 7%, one way or the other. Every time we get an inference problem, I will give you lots of room on a piece of paper like this because there's a lot of stuff to write down. We always write 4 categories. The first category at the top is we do the state. Then we have the plan. We will have the do. And we'll have the conclude. There will be 4 parts to every inference problem. And we try and standardize this so that you don't forget things. The state, you just have to restate what's actually being asked. What are they telling us to do? And it's almost always the last sentence with a question mark. Almost always the last sentence with a question mark. There's the question mark. I'm just going to read the last sentence again. There's too much stuff up there to kind of take it all in at once. What is the probability that a simple random sample of size 125 will give a result within 7 percentage points of true value? Hey, that sounds awesome to me. What is probability that sample of 125 will give results within 0.07 of the true value? The plan part is where you have to check your conditions. Every time I write conditions, I go just like this. IRONS. 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 For the type of inference we're doing right here with a proportion, we're not really out of time, are we? We got like 25 minutes. Sweet. Okay, under the conditions, you don't have to worry about the I, you don't have to worry about the O, and you don't have to worry about the S. There are only 2 things that you must make note of. The R. Gosh, do I remember what R stood for? Glad I wrote that down over here. R. Random sample. Was this a random sample? Oh, sweet, right there. SRS means simple random sample of size 125. Therefore, here I just write sample was random. And then I go, check. We were working from a random sample. That's a good thing. Then there's the N part. The N stood for, was our data approximately normal? Did we sample enough? Is my sample size of 125 going to be big enough in order to guarantee that we're approximately normal? These are the 2 things that have to be true. NP and N times 1 minus P have to be bigger than or equal to 10. So I'm going to write it this way. NP equals, N is my sample size. That's 125. And the probability that I know is really truly it was 80%, 0.8. N times 1 minus P is 125. Let's see, 80%, 1 take away 80% leaves you 20%. That would be 0.2. This means the expected value, whatever 125 times 0.8 is, 125 times 0.8 is right on the dot 100. 125 times 0.2. 25. These are the expected numbers of kids that say, if I go out and do a sample of 125, this is how many expect to say, yep, I'm going to college. 4 years. Nope, I'm not doing that. Those people are dumb. They're spending $80,000 a year on an education that I can get in the library for free. Okay? For some people, that's true if you happen to be good Will Hunting. Okay? Are these numbers both 10 or bigger? Both greater than or equal to 10. Therefore, approximately normal, and go, check. Those are the two things you had to check. Did you get a random sample, and did you sample enough? Okie dokie. All right, let's go over here to the do part. We actually do some math now with this bell curve. Every time I deal with a bell curve, it's not sometimes, I have a raw, I have a z, I have a percent. The number that goes in the dead center right here is whatever they tell me the true one is. Here was the answer to that. In her district, the planning to attend four-year college, suppose that 80%. We know it's really 0.8 right there, 0.80. That's the real true blue number. If you're going to be within 7 percentage points of that, that means 0.73 and 0.87 are my top ends. We're going to find that probability right there. Can we find that probability? I can totally find that probability. And then we can answer the person's question. We're going to use this equation, z equals x minus mean over standard deviation. I think I'll just do this one on this side. 0.87 minus 0.80 over, this is the crazy one. This standard deviation down below they didn't tell us, but I gave you the formula for it right there. This whole big mammer jammer is going to go on the bottom of that fraction. I recommend you make a decent sized fraction bar. This is going to be 0.8 times 1 minus 0.8 or 0.2 over 125, and that whole thing gets square rooted. That's the standard deviation that goes on the bottom because we have a formula for it. Okay, grab your calculadora and let's get cozy with it.
0.8.
Whatever you got to take to be comfortable with your calculator. Bag of potato chips,
1 minus
my favorite pair of sweatpants on the couch,
0.8.
and Netflix, and my calculator. Yeah, that's 0.8. That's 1 minus 0.8 over 125, the sample size. Okay, some advice. You should not do this big giant calculation in pieces. Don't do it one step at a time. Why? Because people will make mistakes. You don't want to screw this up. The best thing I can tell you to do is put this whole big giant thing right here in your screen all at once. All at once. That means you're going to have to learn how to use your fraction bar, and you might not know where it is. So let me help you find it. In the top left-hand corner, right next to the stat plotter and the line equals button, you will see a green F1. You should look at your calculator and find the green F1. Oh, there it is. It's green. It's F1. The way you get to the F1 menu is you got to hit the green button that says alpha first. If you hit alpha, then F1, it'll pull up a little menu right here with fractions in it. You want to choose number 1. Just hit enter. It'll put a fraction bar on your screen. On the top, I'm going to put 0.87 minus 0.80. On the bottom of the fraction bar, I'm going to start off by making the giant square root symbol. It's going to look really small at first when I put that square root down there, which is just above the x squared button on the left-hand side. Am I going too fast? Do I need to back up? Inside that square root, before I start typing numbers, I'm going to put that other fraction bar. That means I got to go back to the F1 menu. Whoops. Oh, darn it. I screwed up. Okay, I'm still right there. Okay, now back to my F1 menu, put a fraction bar in there. The top of that, I'm going to put 0.8 times 0.2, or 1 minus 0.8. On the bottom of that, I put 125. This is what I mean by put the whole thing in at once. If you just do parts of this at a time, you'll totally screw it up. It's too many operations to try and keep track of. When you hit enter, we get a z-score of 1.956. How do I feel about that 6? Do I want to round it? I'm going to call mine 5.7 because I rounded it up. This is what it looks like in the calculator. Okay, does anybody want me to back up and do that thing again with the F1 button and the fractions and all that stuff? Are we good? You good? Yeah? Yes? Mr. Kurz, you good with that fraction button and stuff? Hopefully you got this number on your screen. Okay, the z-score right here is 0. That's the 50th percentile. This one is 1.957. What's nice about the bell curve being totally symmetric, if this is a z-score of 1.957, do I have to do a whole nother set for this dude? No, because that's 7% above, 7% below. This would be negative 1.957. Now that I have z-scores, I can do a normal CDF from negative 1.957 to 1.957, and we should get a probability. Let's see. Normal CDF, negative 1.957. Whoa, I screwed my decimal 0.957 to positive 1.957. 0, 1 for my z-scores. Type in my answer. I get this. %. That's the answer to the person's question way up here at the top. What was the probability the sample of 125 is going to be within 0.7 of the true value? About a 95% chance that the sample will yield an answer and within 7% of 0.8. That means there's about a 5% chance that they're going to go out there and take a sample, and they're going to be off by at least 7% one way or the other. I never feel good about 95%. But people look at me like 95%, that's like an A on a test. I like to get A's on tests, right? You feel good about 95%? The first thing that always comes to my mind is, so if you made it to school alive 95% of the time, you down with that? It's once every 20 days you die. So is 95 good? And it doesn't feel so good anymore. Okay, this problem that we just completed together is a template for how to attack this problem about vouchers. Are you guys down with vouchers? Do you even know what vouchers are? You know what vouchers are? Maybe not. That's okay. I can tell you. All right, so does anybody know anybody that attends school up at LC? Anybody know anybody at Lenny Christian? One name. I just need a name. One name.
Paige DeVelden.
Okay. Paige goes to school at LC, right? She got parents. Do you know how much they pay for her to go there? About 10 grand.
A year?
A year. About $10,000 a year. However, Paige's parents also pay taxes on their property taxes and sales tax for anything they buy to run Linden Public School or Meridian if they live in this district. Right? Do they live in the Meridian district? They paid money for this. Is that fair? What do you think? should they have to pay for you to go to school? That's what the concept of a voucher is. So most of the private schools in the state have been trying to legislate for forever and trying to get a law passed that says, you know what? The amount of money that they pay to this district to send their kids here, they should get like a refund check if they're going to send their kid to the private school. Just give me my $7,000 back or $8,000 or whatever it is to pays for this building, and then I'll take that and it'll go right to Linden Christian Public Schools. Is that fair? That's what they're arguing. And they don't even want 10 grand. They don't even want 7 grand. They're like, I'll just take a check for 2. Give me $2,000 back. I'll be good with 2 grand. Can I have 2 grand back, please? And then I'll take that and I'll give it to Linden Christian. Okay. That's what a voucher is. Okay. Vouchers are controversial stuff. What about the Northwest Road over there? Do I pay taxes for the Northwest Road to be there and be flat and have stop signs? What if I pledge never to drive on Northwest Road? Should I get a refund? How about I-5? I never drive on I-5. Therefore, I should get a refund because I never use it. So that's the counter argument that if you choose to send your kids to a Christian school because they want some form of non-secular education, well, that's your choice. You can't get out of paying your taxes by that argument. So anyway, that's what a voucher is. A voucher is, and that's true. In some states, people get vouchers back. Usually not for the entire amount that they pay in taxes for the schools, but they get something back, but they don't really get it back. It goes directly to the school. So they wouldn't get a check in their hands and they hand it to the school. It would go directly from the state to LC. Yes, ma'am.
Is it kind of the same like a rain check type of thing? Like if you go to the store and you get a rain check?
Sorta. It's like a kickback. Yeah, totally. I see what you mean. Yeah. But that's what vouchers are. Okay, so we're talking about vouchers here. An opinion poll asked a sample of 500 adults whether they favor giving parents of school-age children vouchers that can be exchanged for education in any public or private school of their choice. This also has another impact. Did you guys know that Meridian School District has a higher percentage of non-resident students than any school in the county? There are more people that live in Whatcom County that don't live in the Meridian School District that send their students here to go to school. They totally do. That's because it's super popular to come to Meridian. People want their children to come here. Now, you can make arguments why that is, but that's the reality. And so if I live over in the Ferndale School District and I pay taxes in the Ferndale School District, but I want my kid to go to Meridian, where should my local property tax go? Should the property tax that I pay in Ferndale go to the Ferndale School District, or should it come to Meridian because that's where I send my kid? That's the same kind of thing. You get a voucher as a parent. I want my kid to go to that school, so my kid goes there and the check follows them. Fair enough? So it's not just public. It could be, or not just private, but it's also public schools. Okay, we're going to go out and we're going to ask 500 people about vouchers. Okay, do you support vouchers? Each school will be paid by the government on the basis of how many vouchers it collects. Suppose that, in fact, okay, we're telling you 45% of the people are in favor of vouchers. That means 55 against. Maybe it's less than 55. Maybe there's some like, I abstain. Are we out of time?
No.
We got 10 minutes. Okay, good. We got 10 minutes. Okay, this 45 right here, I'm going to tell you, goes right there. That's the dead center. We know that it's 45% is the middle. This is my raw. This is my Z. This is my percent. We are going to calculate the probability based on a sample of 500 people that we go out and we take a sample. What is the probability that more than half of the sample are going to be in favor? That means we're going to be off of the 45%. And what happens when somebody takes an public opinion poll and more than half the people are in favor of it? That's pretty good evidence that we should have vouchers, right? So the question is it's really 45. Is it possible to go out and take a sample that's off by 5%? What you're calculating here, folks, is this. What is that probability right there? Because it could happen. You could take a public opinion poll that shows support for something that people really don't support. All right, your task. State, plan, do, conclude. You can use the previous one as a model. and see if you can come up with a probability. What is this probability over here? If you get stuck, you need some assistance, just give me a holler. I got the answers right here in my hot little hand. Are you sure? I think it does. Right there. You know those three letters?
Oh, I didn't see, I just read right over.
I understand. Again, if you're stuck, you're not sure what to do, give me a holler. Use the previous page as a template, man. It's right there. Should look just like it.
I actually think that I wanted to.
Okay. That came from doing 1 minus 4. Maybe so if it was 0.8 for this, 1 minus that 0.2 is bad. If I want to do that R under 10%. So if it was 0.4 on that, that would be 0.55 or 1 minus 0.45. So if it's 45 and 55%, there's roughly yes and no percent.
Yeah.
This is correct so far.